Hello everyone, thanks for tuning in. My name is Lucian Cojocar and I'm a postdoc at Microsoft Research. Our paper is titled, Are We Susceptible to Rowhammer? An end-to-end methodology for cloud providers. This is joint work with Jeremy and Minesh, two summer interns from ETH Zurich, where they are advised by Professor Onur Mutlu, and Lilian Tsai, an intern from MIT, and Stefan and Alec from Microsoft Research. In the past 6 years, many papers have shown a plethora of Rowhammer attacks affecting operating systems, virtual machines, trusted environments like HGX, browsers, network protocols, and so on. These papers showed Rowhammer attacks on all types of DDR memory, even including DRAM equipped with error correction. DRAM disturbance errors violate the hardware and software-enforced security boundaries we rely upon in today's systems. A program, just by accessing its own memory, can corrupt pages belonging to another program on another virtual machine. It is no surprise that people are fascinated about Rowhammer and that media did not hesitate to capitalize on this fascination. While there are many research papers on Rowhammer, there are even more media articles describing Rowhammer attacks and predicting doomsday scenarios. Each time Rowhammer made the news, memory vendors did not hesitate to make all sorts of claims. These claims all follow the same template. Rowhammer only affects our old DRAM chips. Our new chips we're currently selling are perfect. You can't Rowhammer them, trust us. When the initial research papers on Rowhammer were first published, memory vendors claimed that the new DDR4 is Rowhammer free. These claims are all false. The security community quickly dispelled these myths and Rowhammer was shown to affect all types of DDR DRAM. This avalanche of claims made multi-tenant cloud providers very nervous about Rowhammer for two reasons. First, Rowhammer is a very serious security attack because it requires no special privileges. Anyone can get a VM in the cloud and start hammering. A successful attack can cause a cloud server to reboot, or even worse, to be compromised. The second problem is that media articles portray the cloud as defenseless in the face of Rowhammer. Cloud providers are very concerned by the prospect of unstoppable security attacks. Some skeptics even point out the lack of evidence of Rowhammer attacks being mounted in practice. If the threat of Rowhammer is so imminent, why there are no attacks known in practice? As a result, multi-tenant cloud providers have a difficult time understanding whether their infrastructure is susceptible to Rowhammer attacks. Our work helps the cloud providers by developing an end-to-end methodology to test if any server is susceptible to Rowhammer. During the development of this methodology, we overcame two major technical challenges. First, we developed an instruction sequence to hammer DRAM at near optimal rate. The instruction sequences used in previous work all hammer DRAM at rates far from optimal. Second, we developed a strategy to map the row adjacency inside DIMMs. Finally, we applied our methodology to 3 generations of Intel servers from a multi-tenant cloud provider. In today's talk, I will focus only on results from Intel's Skylake architecture, which is one of the most popular architectures used in data centers today. Before going into details, let's have a short primer on Rowhammer. In 2014, a study of more than 100 DDR3 DIMMs coined the term DRAM disturbance errors. They show that aggressive DRAM accesses can cause bits to flip. On the left-hand side, we present a short instruction sequence that loads two addresses, A and B, and then flashes them from the cache. These 4 instructions are done in a loop millions of times. A and B are carefully chosen to map in DRAM to two different rows called aggressor rows. These two aggressor rows surround the victim row. On the slide, the aggressor rows are row 1 and 3, and the victim is row 2. The CPU issues DDR commands to the DRAM over the fast DDR bus. To read data from the alternate rows, the CPU sends DDR activate commands. In our animation, the CPU activates rows 1 and 3 alternatively. This sequence of activates can cause bit flips in the victim row, row number 2. The higher the activation rate, the higher the likelihood of bit flips. Let's dive in. To identify Rowhammer failures, our testing methodology must replicate the worst-case Rowhammer testing conditions. We identify two fundamental requirements to accomplish this. First, our methodology must generate the highest rate of row activations. Second, our methodology must make sure that the aggressor rows surround the victim. Inside of the DRAM device, the two aggressors must be adjacent to the victim row in order to create worst-case testing conditions. Let me start by explaining how our methodology meets the first requirement. Previous work evaluates the effectiveness of Rowhammer instruction sequences by counting the number of flipped bits. Unfortunately, this metric is inadequate for testing DRAM because it fails to distinguish the case where memory is safe from the case where the instruction sequence is unable to generate a high enough activation rate to cause bits to flip. To optimize for the highest rate of activations, we first need a reliable way to measure the rate of activations. In our work, we use a DDR4 bus analyzer that allows us to see the full picture of how the memory controller communicates with DRAM by interposing between the CPU and the DIMM. This allows us to observe the exact address and timing for every DDR command, including row activations. Another challenge is that the effectiveness of an instruction sequence is influenced by many factors. I won't talk about all of them, but at a high level, out-of-order execution and CPU caches make it difficult to generate a high rate of DRAM activations. It is no surprise that a plethora of Rowhammer instruction sequences were shown to cause bits to flip on one machine, but were less effective on another. While many different Rowhammer instruction sequences have been used, they all follow a variant of the following template. In a loop, the CPU executes two memory reads. The addresses are chosen in such a way that they correspond to two different rows in the same bank. Then the cache is flushed to ensure the reads in the next loop iteration bypass the cache and reach DRAM. Finally, the instruction sequence may contain a memory barrier that ensures a proper serialization of the accesses across loop iterations. Because the memory barrier has different behaviors on different microarchitectures, all possible combinations were claimed to yield results. This graph shows the performance of four instruction sequences that use the template I just showed. These sequences all use CL-flash-opt, a newer Intel instruction to flash a cache line, and use different types of barriers. For a complete list of the instructions, please consult our paper. The x-axis shows the number of activates within a refresh interval. A higher number is better for our purposes. The numbers are reported as cumulative distribution. The optimal rate of row activates is 167.4 per refresh interval. We observe that the instruction sequence that uses no memory barrier is the closest to the optimal. The takeaway message is that previous instruction sequences are at best 33% from optimal. The activation rate for instruction sequences that use CL-Flash is even lower than what we show here. In our work, we experimented with a plethora of different instruction sequences to find a way to maximize the rate of row activations. During this process, we discovered that cache line flash instructions can cause memory accesses. We ended up with the following instruction sequence composed simply of two CL-Flash opt instructions in a loop. Intel's documentation shows that the reason for CL-Flash opt triggering a memory read for systems with multiple processors is that cache coherence information for each cache line is stored within the line itself in DRAM. This instruction sequence is highly surprising because it has no explicit load or store instructions. The gap between its performance and the optimal is due to conflicts with ongoing refresh commands. Specifically, this gap represents the time it takes for DRAM to execute the refresh command. Now that we know how to generate the highest rate of activations, 2CL flash opts in a loop, let's focus on our second requirement. That is, finding rows that are physically adjacent in a DRAM device. To find row adjacency, we need to understand each layer in the system that deals with memory addresses. The translation from virtual address to a DRAM internal address decomposes in several layers: virtual to physical, physical to a DDR bus address. A DDR bus address specifies which row, column, and which bank the CPU wants to access. Lastly, the DDR bus address decomposes to a DRAM internal address. While the upper layers are well understood by the research community and sometimes are documented by CPU vendors, the internal addressing of DRAM is a highly guarded trade secret. What is even worse, the internal addressing can change from one DIMM vendor to another. This forces the cloud provider to extract the adjacency map for each hardware he wants to test. Our second challenge boils down to understanding the last two layers. For this, we use the methodology introduced in previous work, mounting a devastating Rowhammer attack and then mapping the locations of the bit flips. In a devastating Rowhammer attack, most bit flips occur in the row adjacent to the aggressor row. When hammering one row, say row k, then row k-1 and k+1 flip many bits. Then k-2, k+2 flip fewer bits, and so on. As a result, we can reverse engineer adjacency patterns by mounting devastating Rowhammer attacks. However, this approach works only for DIMMs that succumb to Rowhammer, so it becomes a bit of a chicken and egg problem. Here's how we mount a devastating Rowhammer attack on any server. Recall that the memory controller periodically sends refresh commands to the DIMM. The insight is that in the absence of memory refreshes, electrical charges that encode the bit values in memory cells slowly fade away. This makes any DIMM to succumb to Rowhammer. To keep our work applicable to any server, our methodology proposes a server-independent way to block refreshes. Essentially, we develop a device that acts as a firewall. This device masks the refresh commands while allowing Rowhammer-related commands such as activates to pass. To do this, we designed a hardware fault injector that allows us to control whether or not refreshes are seen by the DIMM. When the push button is pressed, all refresh commands are masked and do not reach the DIMM. This device works by faulting one of the signals on the DDR bus, hence its name, the fault injector. We designed the other switches to restore the communication between the CPU and the DIMM after the refreshes are masked. You can find more details about this challenge and the fault injector in the paper. This is how our testing hardware stack looks like. At the bottom, you can see our fault injector. In the middle, we have the interposer for our bus analyzer. On top of that sits the DDR4 DIMM for which we reverse engineer adjacency. Let's look at the map recovered with our fault injector. This graph shows a single column across many different rows. On the left, you can see the row addresses. These row addresses are part of a DDR bus address. This single column comprises of 64 individual bit lines spanning across all rows. Each 64-bit group forms a memory word, and the number represents the bit position within a 64-bit word. Here we display only a single column, but the same behavior is true for the rest of the columns. We discovered two classes of adjacency. Let me explain. First, we discover rows for which the adjacency is straightforward. For example, row B has two rows adjacent, row A and row C. We call these two rows fully adjacent to the aggressor row. However, this is not always the case. Now let's look at row F. We discover row E to be fully adjacent to row F. Surprisingly, we discover another two rows that are adjacent to row F. These two rows are 10 and 0. But not all the bits from these two extra rows are adjacent to the bit in the aggressor row. To be more precise, one half of a 64-bit word from row 10 is adjacent with row F, and the other half of the 64-bit word from row 0 is adjacent with row F. We call these two rows half adjacent to row F. This has implications on the row addresses that an attacker needs to hammer. To target every cell in row F, a double-sided Rowhammer attack would need to activate 3 rows instead of 2. The attack needs to activate row E, but also the two halves, row 10 and row 0. An additional challenge to mounting a Rowhammer attack is that this map changes from one device to another. This is the map for another vendor. Our fault injector solves the second challenge by allowing cloud providers to map the physically adjacent cells in a DIMM. There are two takeaways from this slide. First, the row address map is not always linear. Second, this map is different from one DIMM to another. This slide shows the map changing from one vendor's device to another, but although we haven't done a rigorous characterization, we anticipate these maps to change from one DRAM generation to another, even for DIMMs sourced from the same vendor. Please read our paper for many additional results. For example, we investigate whether bit positions or data patterns affect the susceptibility of DRAM to Rowhammer. To summarize, we developed an end-to-end methodology to test if any cloud server is susceptible to Rowhammer. First, we introduced an instruction sequence based on CL-flash opt that hammers at near optimal rate. With the help of a bus analyzer, we showed that on Skylake, our instruction sequence hammers at near optimal rates, while other proposed instruction sequences are far from optimal. Second, we devised a strategy to map row adjacency inside DIMMs. We developed a hardware fault injector that masks refresh commands, and we showed that logical rows do not always map linearly. Finally, we applied our methodology to three generations of Intel servers: Broadwell, Skylake, and Cascade Lake. You can find all these results in our paper. Thank you for your attention.